Okay, we're ready to go. All right, so we are in chapter 3, section 1 on matter. Is everybody ready? I think I am.
Science Notebook. 1. Properties of matter. Picture a glass of ice water. The ice floats, and you know the ice will eventually melt if left long enough at room temperature. When the water changes from solid to liquid, does the composition of the water also change? Review vocabulary. Density, a ratio that compares the mass of an object to its volume. New vocabulary. States of matter, solid, liquid, gas, vapor, physical property, extensive property, intensive property, chemical property. Main idea. Most common substances exist as solids, liquids, and gases, which have diverse physical and chemical properties. Essential questions. What characteristics identify a substance? What distinguishes physical properties from chemical properties? How do the properties of the physical states of matter differ? Substances. As you know, matter is anything that has mass and takes up space. Everything around us is matter, including things we cannot see, such as air and microbes. For example, table salt is a simple type of matter that you are probably familiar with. Table salt has a unique and unchanging chemical composition. Its chemical name is sodium chloride. It is always 100% sodium chloride, and its composition does not change from one sample to another. Salt harvested from the sea or extracted from a mine, as shown in Figure 1, always has the same composition and properties. Recall that matter with a uniform and unchanging composition is called a substance, also known as a pure substance. Table salt is a pure substance. Another example of a pure substance is pure water. Water is always composed of hydrogen and oxygen. Seawater and tap water, on the other hand, are not pure substances because samples taken from different locations will often have different compositions. That is, the samples will contain different amounts of water, minerals, and other dissolved substances. Substances are important. Much of your chemistry course will be focused on the composition of substances and how they interact with one another. Figure 1. Whether harvested from the sea or extracted from a mine, salt always has the same composition.
Okay, so basically what it did first was it was telling you what matter was, okay? Matter is anything to take up space. We've heard this about 15 times, have we not? Okay, so that's basically what it was talking about. And then it was talking about substances and what pure substances are. What is a pure substance?
Like salt or like water. Temperature.
What is a pure substance?
Salt.
Element. Okay? If you're talking about salt, sir, that's Na, right? That is also a pure substance. Okay? But here we are. Sodium chloride is mainly what salt's made out of, which is NaCl, which is a mixture. Water, H2O, is H, hydrogen, and oxygen together, which makes it a mixture. So be careful on the way that they're wording that because they're kind of a little bit confused, aren't they?
Yes, ma'am. So,
Okay.
The salt that's in the ocean, is that the same salt we put with?
Yes. We do. You can use that salt, or you can get it from a salt mine.
Oh,
It's in the ground.
It's everywhere.
Yes,
The salt you got in the ground, that's like rock salt, though, ain't
it
it?
is.
And the sea salt is salt out of the ocean.
Oh my God! Listen to him. He's brilliant. Yes.
Okay.
No, he is. Did you hear him? I love that. I've never used that analogy. I like that. Salt water.
States of matter. Imagine you are sitting on a bench, breathing heavily and drinking water after playing a game of soccer. You are in contact with 3 different forms of matter. The bench is a solid, the water is a liquid, and the air you breathe is a gas. In fact, all matter that exists naturally on Earth can be classified as one of these physical forms, which are called states of matter. Each of the 3 common states of matter can be distinguished by the way it fills a container. Scientists also recognize other states of matter. One of them is called plasma. It can occur in the form of lightning bolts and in stars. Get it? Name the common states of matter. Solids. A solid is a form of matter that has its own definite shape and volume. Wood, iron, paper, and sugar are all examples of solids. The particles of matter in a solid are tightly packed. When heated, a solid expands, but only slightly. Because its shape is definite, a solid might not conform to the shape of the container in which it is placed. If you place a rock into a container, the rock will not take the shape of the container, as shown in Figure 2. The tight packing of particles in a solid makes it incompressible. That is, it cannot be pressed into a smaller volume. It is important to understand that a solid is not defined by its rigidity or hardness. For instance, although concrete is rigid and wax is soft, they are both solids. Liquids. A liquid is a form of matter that flows, has constant volume, and takes the shape of its container. Common examples of liquids include water, blood, and mercury. The particles in a liquid are not rigidly held in place and are less closely packed than the particles in a solid. Liquid particles are able to move past each other. This property allows a liquid to flow and take the shape of its container, as shown in Figure 3, although it might not completely fill the container. A liquid's volume is constant, regardless of the size and shape of the container in which the liquid is held. The volume of the liquid remains the same. Because of the way the particles of a liquid are packed, liquids are virtually incompressible. Like solids, however, liquids tend to expand when they are heated. Get it? Compare the properties of solids and liquids in terms of their particle arrangements.
Okay.
Figure 2. A solid has a definite shape and does not take the shape of its container. Particles in a solid are tightly packed. Figure 3. A liquid takes the shape of its container. Particles in a liquid are not held in place rigidly.
Okay. So on your desk, I gave you this handout. Does everybody see it? Okay, let's take the handout out. So what we've learned so far is states of matter with solid and liquid. Right, guys? Now, on this paper, it says particle arrangement, particle energy, and other information. Okay. What are we going to put in for a solid and a liquid as far as the particle arrangement? Okay.
Matter.
What I want you to do is I want you to draw this box. What this is a container. Okay. This is a beaker. Everybody ready?
Solid and liquid.
So solid and liquid, and I'm on the first box. How can I draw what a solid and a liquid looks like as far as molecules go that would make sense to you?
So you could draw like little dots in a square. They're all tight together, but it's not taking like the shape of the glass for a solid. So almost like a square. It's like a solid object.
That look good?
Yes, ma'am.
And then
Right.
for a liquid, you could do them like they're kind of spread out, and it takes more of the shape of the container.
Okay. Everybody got it so far? So right now in the first box, you're going to draw that for the solid. For a liquid, you're going to draw that in the first box. Is everybody good so far? So we're drawing a beaker. Solid has it all chunk in the middle. Liquid has it all the way across. Everybody good so far? Okay. Next box says particle energy. What does that mean? If we looked at them atom-wise, how would the particles be moved in a solid? Slow. Okay? Can't hardly even see it. Do you know what I mean by slow? You know that sloth that takes forever before it moves?
Yeah.
That's the movement. So write slow or very, very slow underneath the particle energy.
For both of them?
Nope, just for a solid. I put slow.
Yes.
Can't even see it move. Can't even see move. All right. How about a liquid?
You see it moving.
It's moving, right? But it's not moving very fast, is it?
That on.
Okay. So it is moving slowly.
I don't know, you ever like a picture of tea over it, move pretty fast.
Yes, but what we're talking about is this. When you're looking at a liquid, sir, you are seeing hydrogen and 2 oxygens together. All right, sir? And what they're doing is they're slowly moving, but they're making a liquid. Okay? Unless acted on by an outside force if you hit it. You got it? Good so far? Okay? Now, what do we want to put in for other information?
I really don't know.
Okay? A solid has a definite shape.
You can compress the salt like you can mash a solid, but if you try to mash a liquid, it's just gonna move.
So it definitely has a definite shape, right? What other thing did it say in the book?
Solid.
And volume. You're right. Definite shape and volume. Because it doesn't change at all, does it? Okay? How about a liquid?
It can change because it changes to fit whatever container.
Okay, there we go.
I take
Fit
water out of a bottle and pour
the-
it in a cup, it changes.
Yes, sir. Container. So write that. Does that pretty much cover everything that we could have written in our book?
Just about.
Pretty much, right? So I still went in and put states of matter. I did a solid and a liquid, and I just wrote a couple of notes about that. And now we're going to go on to the next page. So let's flip our book to the next page, please.
Gases. A gas is a form of matter that not only flows to conform to the shape of its container, but also fills the entire volume of its container, as shown in figure 4. If you flow gas into a container and close the container, the gas will expand to fill the container. Compared to solids and liquids, the particles of gases are far apart. Because of the significant amount of space between particles, gases are easily compressed. You are probably familiar with the word vapor as it relates to the word gas. However, the words gas and vapor, while similar, do not mean the same thing. They should not be used interchangeably. The word gas refers to a substance that is naturally in the gaseous state at room temperature. The word vapor refers to the gaseous state of a substance that is a solid or a liquid at room temperature. For example, steam is a vapor because water exists as a liquid at room temperature. Get it? Differentiate between gas and vapor. Figure 4. Gases take the shape and volume of their containers. Particles in a gas are very far apart.
Okay. So on our paper, we got one more box to fill, right? That's going to be, well, 2 really. Gas and plasma, right? So let's do gas. Now, the particles are going to be spread out, correct? It actually fills the volume of whatever you put it in, right? That's the other characteristic that I had.
You have to have enough of it to do that. Don't feel like you're trying to fill a balloon, but you don't have enough air to fill it. It's not going to fill all the way.
Well, it will inflate it if it gets warm. So in other words, I had this experience when my daughter was, I think it was her 21st birthday. I was driving a little car, and it was in the middle of the summer. Her birthday's in August. So I told the people, do not fill the balloons up completely. Leave some room. Because when it got in the car and I knew it was going to sit in the car, it expanded. It didn't, because we didn't fill it up all the way. Because I was smart enough. And I knew it was going to be outside, so I needed to do that. So technically, you are right, but do you understand where the error is? Good. Okay. Plasma, we're not worried about. We're not doing anything with plasma on our paper. Is everybody good so far? Okay. Let's go ahead and go to the next page.
How would your daughter know this one?
Real world chemistry, physical properties, minerals. Scientists use physical properties such as color and hardness to identify minerals. For instance, malachite is always green and relatively soft. Malachite was used as a pigment in paint and is now mainly used to make jewelry. Physical properties of matter. You are probably used to identifying objects by their properties, their characteristics and behavior. For example, you can easily identify a pencil in your backpack because you recognize its shape, color, weight, or some other property. These characteristics are all physical properties of the pencil. A physical property is a characteristic of matter that can be observed or measured without changing the sample's composition. Physical properties also describe pure substances. Because substances have uniform and unchanging compositions, they also have consistent and unchanging physical properties. Density, color, odor, hardness, melting point, and boiling point are common physical properties that scientists record as identifying characteristics of a substance. Table 1 lists several common substances and their physical properties. Get it? Define physical property and provide examples. Extensive and intensive properties. Physical properties can be further described as being one of two types. Extensive properties are dependent on the amount of substance present. For example, mass is an extensive property. Length and volume are also extensive properties. Density, on the other hand, is an example of an intensive property of matter. Intensive properties are independent of the amount of substance present. For example, the density of a substance at constant temperature and pressure is the same no matter how much substance is present. A substance can often be identified by its intensive properties. In some cases, a single intensive property is unique enough for identification. For instance, most of the spices shown in Figure 5 can be identified by their scent. Figure 5. Many spices can be identified by their scent, which is an intensive property. Infer. Name an extensive property of one of the spices pictured.
Okay. So I'm going to give you a couple of minutes to write this down. Aaron, please. Okay. So extensive properties. You want to write down that it depends on the amount of substance of that is present. The examples of extensive properties is mass, length, and volume.
Can you repeat that again, sir?
Yes, sir. Extensive properties depends on the amount of substance present. Examples are mass, length, and volume.
Want weight we want to or no?
No.
You said length and what?
Mass, length, and volume.
Well, I just wonder how come weight won't be one if length is one.
Weight,
Yeah.
it's the same thing as mass.
Oh,
When you're doing a substance, you're looking at mass. You're good. And then intensive property, independent of substance present. And what is the one example they gave us for an extensive one? I mean, intensive one. No, it gave us one that was an intensive property. Density. Please write that down. Next page.
chemical properties of matter. Some properties of a substance are not obvious unless the substance has changed composition as a result of its contact with other substances or the application of thermal or electric energy. The ability or inability of a substance to combine with or change into one or more other substances is called a chemical property. Iron forming rust when combined with the oxygen in air is an example of a chemical property of iron. Similarly, the inability of a substance to change into another substance is also a chemical property. For example, when iron is placed in nitrogen gas at room temperature, no chemical change occurs. Get it? Compare physical and chemical properties. Observing properties of matter. Every substance has its own unique set of physical and chemical properties. Figure 6 shows physical and chemical properties of copper. Copper can be shaped into different forms, which is a physical property. When copper is in contact with air for a long time, it reacts with the substances in the air and turns green. This is a chemical property. Table 2 lists several physical and chemical properties of copper. Figure 6. One of the physical properties of copper is that it can be shaped into different forms, such as the wires on circuit boards. The fact that copper turns from reddish to green when reacting with substances in the air is a chemical property.
Okay. Physical property has to do with extensive and inextensive property, right? What it looks like, mass, melting point, what you see, smell, or taste. Everybody good with that? When we're talking about chemical properties, as it says here, ability and or inability for a substance to combine with another or change into one in another substance. Okay, so make sure you understand that. We're going to go to the last page of our reading assignment, and I think we'll be done today because I have pushed you to your breaking point.
Is that why the Statue of Liberty, like, it turned green because it's made out of copper and it's like oxidized with the air?
Yes, sir.
He's very smart.
I know. He's on a roll today. I'm telling you, I think I just need to take
Vocabulary. Academic vocabulary. Resource. A source of information or expertise. The library contains resources for many different subjects. Properties and states of matter. The properties of copper listed in Table 2 might vary depending on the conditions under which they are observed. Because the particular form or state of a substance is a physical property, changing the state introduces or adds another physical property to its characteristics. It is important to state the specific conditions, such as temperature and pressure, under which observations are made, because both physical and chemical properties depend on these conditions. Resources that provide tables of physical and chemical properties of substances, such as the CRC Handbook of Chemistry and Physics, generally include the physical properties of substances in all of the states in which they can exist. Consider the properties of water, for example. You might think of water as a liquid, physical property, which is not particularly chemically reactive, chemical property. You might also find that water has a density of 1.00 grams per cubic centimeter, physical property. These properties, however, apply only to water at standard temperature and pressure. At temperatures greater than 100 degrees Celsius, water is a gas, physical property, with a density of about 0.0006 grams per cubic centimeter, physical property, that reacts rapidly with many different substances, chemical property. Below 0 degrees Celsius, water is a solid, physical property, with a density of about 0.92 grams per cubic centimeter, physical property. The lower density of ice accounts for the fact that icebergs float on the ocean, as shown in Figure 7. Clearly, the properties of water are dramatically different under different conditions. Figure 7. Because the density of ice is lower than the density of water, icebergs float on the ocean.
Okay. All right, so what I would like you to do now, let's go back and make sure we understand what we need to submit today.